All right, we're going to continue our discussion about vectors with what we call the dot product. So I had mentioned in the last lesson that we really don't have vector multiplication like we would think of normal multiplication. So we use the symbol that looks like multiplication, but it's not exactly multiplication. We do multiply within it, but you can see that what we're doing when we find the dot product of two vectors is we're taking the product of their A values and adding the product of their B values. So not exactly like multiplication, but the closest thing that we have when we're talking about two vectors. So dot product we can find this way, or you can also find by taking the two magnitudes and then multiplying by the cosine of theta. Properties of real numbers do apply to the dot product. So you'll see that this multiplication and this addition works just like you would think that it would. When we need to find the angle between two vectors, we do that using this formula here. Again, as I've said in the past several videos, most of these formulas are not ones that are given to you on the formula sheet for the final exam. So I do strongly suggest that you write these formulas out in your box, because I really wouldn't think that you would memorize them. And if they're not in your box and you don't know it, then obviously if they ask a question on the final exam, you're kind of out of luck. So I would never remember this formula without looking at it. So definitely want to make sure that that's in your box. So if we're finding the angle between two vectors, we're going to use the dot product on the top and then divide by the magnitudes. This is really just taking this guy and solving it for theta. So getting it kind of by itself there. All right, so vectors also, we can have vectors that are parallel, and vectors are considered parallel when the angle between them is either 0 or 180 degrees. Now that can create two different situations. Both of them are parallel situations, but if it's 0 degrees for the angle, that means that they're going the same direction. If it's 180, then that means that they're going in the opposite direction of each other. So you might have one vector, going like this and one going like this, because remember that all vectors have both a magnitude and a direction. So it's not just, parallel lines, not exactly the same thing. We also have what are called orthogonal vectors, and vectors are orthogonal if the angle between them is 90 degrees. So this is kind of like perpendicular. The other way to have orthogonal vectors and to be able to prove that they are such is if their dot product is equal to 0. So those are kind of the introductory main things that we are going to find that are pretty simple. The last, second to last, I guess, bullet point here, the vector projection. This one has a lot of steps, and we're going to go through an entire example where we do the vector projection. You'll have some in your homework to practice, and so please make sure you know how to do this. It's not always on the final exam, but I have seen it on the final exam at least once. So it would be prudent to make sure that you know how to do it. So vector projection of vector V onto vector W, it matters, of course, which one is first. When we do the notation, whichever is the onto vector, that's the one that becomes the subscript. The original, the of vector, is the one that becomes like the input. A projection, vector projection, should be parallel to the vector that is onto. So in this case, vector W. We form a vector projection by dropping a perpendicular to the line that goes through both vector W and the terminal point of vector V. So you can draw things to help you. I usually don't need to, but if an illustration helps you, this kind of describes how to do that. We break the original vector v down into components, vector v1 and vector v2. The projection of vector v onto vector w is vector v1. So most often when you have a problem like this, it will ask you to do both things. It'll ask you to find the projection, which really is just this part, and break it down into its vector components, which means just the projection that you already have and vector v2. So it makes sense because vector v is vector v sub 1 plus vector v sub 2, that if you're trying to find vector v sub 2, that's just going to be vector v, the original, minus the projection that you found, which is vector v sub 1. This is the formula that we'll use when we're finding the projection. So remember, this guy is the same thing as vector v sub 1. So finding that uses this. You do the dot product on top of the two vectors, then you take the magnitude of the onto vector and square it, and then you multiply that entire thing times the original onto vector, the one it's supposed to be parallel to. Last formula that we have here doesn't get used a ton, but it's work done by a force, and if we're moving an object from one place to another. So here is our formula for that. You take the force vector times vector from A to B, or that can also be done by finding the magnitude of the force vector, the magnitude of the vector from A to B, and multiplying by the cosine of the angle that's between. All right, so let's take a look at how to use some of these. So example 1, we have vector v and vector w, and the first thing we want to do is to find the dot product. So dot product formula was way up at the top. In this case, because we have the original vectors in ij form, that means we have the a's and the b's. So the easiest way would be to use this one. Obviously, if we had angles and magnitudes, we would use the second one. So it just kind of depends on what we're given. So in this case, we're going to do a sub 1, which is negative 4, times a sub 2, which is negative 2, plus b sub 1, which is 8, times b sub 2, which is negative 6. And that's going to give us our dot product. So that gives us 8 minus 48, which is negative 40. So plug and chug, pretty simple. Part B asks us to find the angle between the vectors. So that's going to be this formula right here. So we've already found the dot product, so I don't need to do that over again. I do need to find the individual magnitudes of those vectors in order to have that. So I already know that my theta is going to be the inverse cosine of, and then dot product goes on top, and then the product of the two magnitudes is what's going to go on the bottom. So I need to find the two magnitudes first. So magnitude vector v is the square root of a squared, so negative 4 squared plus 8 squared. So that gives me 16 and 64, which is the square root of 80. So square root of 80, and there's no need to simplify that because we're going to be putting it into our calculator anyway, so it doesn't really matter if we simplify the radicals in this case because we're going to be using the calculator. Vector w's magnitude, we do the same thing, square root a squared plus b squared, so negative 2 squared plus negative 6 squared in this case. So that gives us 4 plus 36, so square root of 40 for its magnitude. So again, because we're going to be using the inverse cosine feature here, because we know this is not a unit circle value, that just means that we really don't need to simplify any of this. It'd kind of be a waste of our time. So I'm just going to go straight to my calculator. I'm going to do inverse cosine, and then I'm going to use my fraction button. If you have an older version of the calculator where you don't get the fraction button, remember that you'll have to do parentheses within parentheses. Make sure you enclose the numerator and then enclose the denominator so that you keep them separate. So negative 40 was my numerator. My denominator, then I'm going to have the square root of 80 times the square root of 40, and then close the parenthesis for my inverse cosine, and that gives me 135. Make sure it's in degree mode. We are going to list this in degrees. It does come out nicely. So we know that theta equals 135 degrees. And it doesn't always come out nicely. Usually it'll tell you what to round to if indeed you're going to have to round. Example 2, use the dot product to determine if vector v and vector w are orthogonal. So this, if we look back at our definition, they're orthogonal if the angle is 90 degrees, which we haven't been told anything about the angle. We could find it like we did here, but that seems like a lot more work than just deciding if their dot product equals 0. So that's what we're going to do, is we're going to find the dot product. If it equals 0, they're orthogonal. If it doesn't, then they're not. So dot product here, we have 8 times negative 6 plus negative 4 times negative 12. So that gives us negative 48, and then gives us plus 48, which is 0. So since the dot product is 0, we would say yes, they are orthogonal. Over here, I'm going to have 5 times, this is just a plain I, so that means that its A value is 1, and then plus negative 5, negative 1. So that gives us 5 plus 5, which is 10. So this one would be a no. So again, most of the stuff, pretty simple. Excuse me, got the hiccups. Pretty simple plug and chug, except for what we do in example 3. And I'm sure you could tell when I was going over the explanation of the projection that we're going to have several different steps. So if I look at the formula, which is right here, I need dot product of vector v times vector w over magnitude of vector w squared, and then I'm going to multiply that all times vector w itself. So once I get all the pieces, I'm going to plug them in, but I need the pieces first. So over here, I'm going to find the dot product. So dot product of vector v with vector w. Oh, and it would probably be helpful if I had written out the vectors, which I didn't. Sorry about that. Let me write them over here. I did type them or write them out on my own. So 3 vector I minus 2 vector j. And then vector w, we're going to do vector I minus vector j. Okay, now we have what we need. So we're going to do 3 times 1 plus negative 2 times negative 1. So 3 plus 2, which gives us 5. So dot product is 5. That's what goes in the numerator up here. Then I need the magnitude of vector w. So square root of, in this case, 1 squared plus negative 1 squared. So that gives me square root of 2. So I have square root of 2 squared. And then I'm going to multiply all this times the original vector w. So vector I minus vector j. All right, so when I square a square root, it just gives me itself. So that just is going to give me a plain old 2. So I have 5 halves in front, which I then need to distribute over my vector. So 5 halves vector I minus 5 halves vector j would be my projection. So this is my answer for projection of vector W onto vector V, or other way around. So that's my projection. I've done the first thing that it asked. Then it says decompose vector V into 2 vectors, vector V1, vector V2, where V1 is parallel to vector W. V2, I didn't mention this in the original. V2 is going to be orthogonal. So when we do this decomposition, it's to get one that's parallel and one that's orthogonal. So remember that vector V1 is the same as the projection, so don't think you need to do extra work for that. You really just need to copy down what we already had written for that. Then I need to find vector V sub 2, and that's going to be vector V minus vector V sub 1. So my vector V, its A value is 3. So I'm going to do 3 minus the A value on V sub 1, which is 5 halves. That's going to go with my vector I. And then I'm going to have minus my negative 2 here for vector V and negative 1. So actually I can just do the plus here and then this. And that's going to go with vector j. So I have 3 minus 5 halves, which is 5 halves, or not 5 halves, sorry. This is 2.5, so that gives me 1/2 vector I. And then because I have, oops, I totally just messed that up. No wonder I was having issues. This should be plus 5 halves here. I accidentally took from vector W instead of from vector V1 here. So it should be V minus the V sub 1. So it's negative 2 minus negative 5 halves. So negative 2 plus 5 halves here. So sorry about that. So negative 2 plus 2.5 essentially, which gives us also 1/2. So I have 1/2 vector I plus 1/2 vector j. That is going to give me my V sub 2. So now what I've done is I've found the projection, and I've also now found the decomposition, which gives me a vector that's parallel to vector W and a vector that's orthogonal to vector W. So now I have both of those. And those are pretty much the toughest ones that you're going to see in the homework. So hopefully that makes sense. Make sure to ask if you have questions.